Now let's go ahead and talk about how to handle experiments that have small sample sizes. So we've talked about how randomized controlled experiments are ideal, and the random assignment to treatment and control works best to make the groups as alike as possible because it eliminates bias. With enough subjects, we've said that random differences average out. But what do we do if we don't have enough subjects? What if we have a small sample and that's all that we have to work with? So, a solution to kind of fix that problem is to look at something called blocking. And blocking is a statistical technique that is used with small sample sizes where researchers will block or divide their subjects into smaller, more homogeneous subgroups first, and then go ahead and randomly divide who gets the treatment within each of those blocks. So I think this is definitely best explained through an example. So our first example is about computer graded versus hand graded homeworks. And it says, suppose I wanted to do a randomized controlled experiment. Good, randomize is best, with a small class of data science students to see if Prairie Learn homework or online homework helps students learn better than hand graded homework. So, where students would actually write on a piece of paper and turn in their homework. Let's say there's 20 students in the class, and we know that 10 of them had A averages and 10 of them had B averages in previous math courses. So, with only 20 students, random assignment into treatment and control could still result in these large accidental differences, making our groups not necessarily as alike as possible. So, for example, we actually did this and we found that we got 8 students with A's in the treatment group and then 8 students with B's in the hand graded group. So our groups were unbalanced in terms of their math grades. And this makes sense for small samples if you think about just flipping a coin. If I flip a coin 10 times, getting 8 heads isn't super unlikely. But if I flipped a coin 1,000 times, getting 800 heads is going to be a lot more unlikely. The more you flip, the more likely you're going to have that balanced group. So here for this example, it says, first of all, with any study, we want to know what's the treatment and what is the response. So I'm going to go ahead and say that the treatment is the thing that we're trying to decide if it works. And this was the Prairie Learn homework or the computer graded homework. So I'm going to say the treatment group is the group that got the Prairie Learn homework. And then the control group got the regular hand graded homework. It also asks what was the response. So the response is kind of the outcome. And the outcome, what we wanted to see was, does it help students learn data science better? So my response is going to be better data science learning. And I essentially want to design an experiment to test, does Prairie Learn homework help students have the response, learn data science better. So it says, why would the two groups be a problem? So, like I said before, in the first group, in the treatment group, we got 8A students. And then in the control group, we got 8B students. So they weren't balanced. So basically, at the end of the study, if we start off with our groups unbalanced, at the end of the study, if they're unbalanced, we don't know if it was because of the treatment or if it was because maybe there were 8A students in the treatment group to begin with. Maybe they were just better students. So it makes it hard to determine if our treatment causes the response. So I'm going to say for this, why would the differences in the two groups be a problem? I'm going to say because at the end of the study, at the end of the study, we don't know if the treatment truly caused the response. It's almost as if our group started off on uneven playing fields. The treatment group had a slight advantage because they had 8A students, whereas the control group had 8B students. So we don't want that to happen. And even though we're doing the randomization, again, we have that small sample, so things like this can happen. So part C says, can you think of a way to ensure the same proportion of A and B students in each group, but still keep that randomization to treatment and control at the end? And this is where blocking comes into play. So basically, what we would do is I'm going to say we would block first, then randomize. So, what I mean by block is basically divide the subjects based on their grades. So, I'm going to take all of the A students. So, for the blocking, I'm going to group all the A students together and then group all of the B students together. And it looks like we had 10 A students and 10 B students. And then within each of those groups, so I'll start with the A students, I'm going to randomly divide half of those to the treatment, half to the control. So I'm going to randomly divide half of them to the treatment group and half to the control. So this kind of ensures, we're still doing this randomly, but ensures we have half of the A students in treatment and half in control. And then I'm going to do the same thing with the B students. So I'm kind of, it's almost like I'm making it so that the groups are equal, but I'm still having that element of randomization. So the next question asks, does blocking introduce bias? And a lot of times when people hear, okay, well, the researcher is dividing the subjects into A and B students, isn't that introducing bias? But because we're ending with that randomization, there actually is no additional bias introduced. And that's why blocking is such a cool tool that we can use to help ensure that our groups are balanced when we have small sample size. So I'm going to say, does blocking introduce bias? No. It says, if so, how? If not, why not? And so I'm going to say no, because we are still randomizing. We're still using randomization. So if the researcher just blocked, if they divided the subjects into A and B students, and then just kind of put half of them in treatment and half in control based on what they wanted to do and didn't use a random method, then sure, that could introduce bias. But because we are ending with randomization, we are good. And then the last question says, is it always better to block first and then randomize, even with large samples? Because we've been talking about blocking as a technique to deal with small samples. And for this, I'm going to go ahead and say it can never hurt. Blocking is never a bad thing. It will never harm you to block. So I'm going to say it can never hurt to block. It can never hurt to block, but I will say it becomes less necessary with large samples, just because with large samples, the randomization should have the differences average out in the long run. So it can never hurt to block, but it becomes less necessary as the sample size increases. So the key takeaway from this video is that blocking first and then randomizing ensures that the treatment and control groups are balanced in regards to the variable that we blocked on. So in terms of students' grades in this example, we know that our groups are going to be balanced. If you think there's another variable that could influence the response, you should definitely block on that variable, especially with a small sample. And you can add, maybe in this example, there's another variable that you think could influence the response. You could also block as many times as you want. So this is a technique that helps us make experimental design the best it can possibly be.